Hello, it's Keith here, and this is lesson 48 of the platform-specific series of my 68000 assembly programming tutorials. We're looking at Mintile today, my multi-platform tile map. Now, on the Genesis, of course, we have a hardware tile map, so really all we're doing is transferring the data from the tile map that Mintile uses that would often be transferred to a bitmap screen, but in this case we're just transferring the data to the hardware tile map. So all we've got today really is a simple example of how to use the tile map on the Genesis. If you aren't doing multi-platform coding, using Mintile doesn't really make any sense. You might as well just go straight to the hardware, and so we'll be seeing that today. Now, we've got a simulated sprite moving around the screen, that Chibico mascot there. That's my character here. That's not actually a sprite, it's just being drawn to the tile map in this example. I am planning a later example of something called Max Tile, which is a more advanced tile map, which is also multi-platform. That does a lot more, and it does do things that will be beneficial to the Genesis, you know, things like creating field tiles to save memory and things. So that will be more interesting as a multi-platform thing. But as I say, today I think is still a great example of a basic tile map example. So here is the code we're looking at today. Now, what we're not going to look at is how to read the joystick, how to move an object around the screen, just, you know, keeping track of variables. Please see my simple series for that. I've covered that before in that series. What we're going to look at today is the stuff related to doing the tiles. Okay, so the first thing is we are sending our pattern data as tile patterns to the VRAM. So we've got our source bitmap address here in A0. We've got the length in bytes here in D1. And we've got the destination memory address in A6 here. Now, each tile is 32 bytes, so we're starting at address 32 here to skip tile 0, which is the sort of default one. We're skipping that. So we are going to use this defined tiles routine. It's not actually changed. If you've seen the simple series, it's still exactly the same on this system. So what we're doing is we're running this prepare VRAM function. Now what this does is it takes our source address in A6 and it moves a bunch of the bits around, and the way it does it is very weird, and you might think, why the heck is it doing that? It's all about Sega Master System compatibility. The Genesis has backwards compatibility with the Master System, and so they've made the memory map for the VRAM work in a way that is compatible with the Master System, and the Genesis has far more memory, so that's meant that the bits have had to be shuffled around all over the place to be compatible. So that's why it is. We've just got these weird shifts we have to do, but we can just use this prepare VRAM to calculate them, and then it moves the final value to the VDP control port, which selects the VRAM destination. Then all we need to do is read in bytes or longs, so 32 bits at a time in this case. All we need to do is load those in here and transfer them to the VRAM, and that will actually define the bitmap data for our tiles here. So this is transferring the tiles to VRAM. They are now in memory. Now on some systems we have to calculate the flipping them. I think on the PC Engine we have to do that. PC Engine doesn't have XFlip for its tile map, but on the Genesis we have all of that kind of thing built in for us, which is why this is such a simple example. Now when it comes to drawing things to the screen, we're either drawing an entire tile map, which will fill almost the entire screen. We have a slight border, but it almost will. Otherwise we have to calculate the VRAM destination within the tile map for our little characters as they move around the screen. So screen base here defines the top left corner of the tile map when we're drawing the entire tile map here. Now we are skipping a few lines here, so we've got plus 64 times 4. That is basically to skip the first few lines, and we're just centering the screen here. You'll see if we run the actual example here. You can see we aren't using the entire screen. It's a 256 by 192 screen, virtual screen we're using. This is for compatibility with the systems with small screens. You can see if I remove those extra bits there, we're now in the top left. So there's actually a lot more screen we could use on the Genesis. But it's all about multi-platform compatibility with these tutorials. That's the point. And this example was ported from a Z80 based example that also exists on the 6502. So we have to make the Genesis to some extent work with the same kind of screen coordinates that the 6502 could do. Now our tile maps are here and here. Now the main background tile map is this one. Now a value of 0 in this is actually an unchanged tile. This is a cache of changes. We're not using a double buffer because some systems don't have the memory to do so. And so basically these values are the tile numbers, but a tile 0 in this area is unchanged, and a tile area 0 in the sprite, which is the tile map of this Chibico character, that is also a miniature tile map. A tile 0 there is a transparent area, so the around the feet there and the top left corner have empty tiles. You can see it's XFlip there, but you can see that empty tile there. Now that's the tile maps that we use to draw our characters into VRAM. Okay, so how do we actually do the job of drawing the characters to screen? Well, if we are not drawing the entire tile map, we need to calculate the VRAM destination using this getScreenPos function. Now the X and Y coordinates within all of my tutorials these days, all the modern ones, use logical units, which are pairs of pixels. The reason for that is, again, I'm working on 8-bit systems a lot, and we want to work with byte coordinates for a 256 pixel wide screen. So we need an off-screen area, so we can't use 1 pixel equals 1 byte, because that would use all the possible values in the single byte, nothing for the off-screen area. So by using pairs of pixels, our logical screen is 128 units across, and that leaves a nice big area for cropping, and that's what we've done here for compatibility. So we are basically taking the coordinates in pairs of pixels here and converting them to coordinates in tiles here, and we're then basically going to take our VRAM screen base, which is the top left corner of our screen. We're going to multiply the X position by 2, because there's 2 bytes per tile definition. We're going to multiply the Y position by 64, because there's 32 tiles on a line and there's 2 bytes per tile, so that's why we're doing that. And basically this calculates the VRAM destination of our tile, and that's what we're doing here. So we've now got the VRAM destination, and when it comes to drawing within Mintile, most of the code is multi-platform. The code that does the cropping and things, all of that is the multi-platform code in the separate series. So if you want to see that, please see my Mintile series. It's got a video series of its own, and basically all that does is it calculates the cropping and anything else required, and it then sends repeated commands to the platform specific code to draw strips of tiles. So the entire screen, or a little sprite, is drawn of individual strips, and they're drawn from left to right. So doStrip will start drawing in a single strip. So what we're doing here is we're loading in the tile number from A2. A2 is our source tile map. If that is 0, we don't want to draw this tile to the screen. It's either a transparent part of the sprite or an unchanged tile in the cache, so we would skip. What we do next is we check tile clear, which is a flag. If this is a 0, then we're going to do nothing. If it's a 1, then we're going to clear the tile that we just read in for. That's if we're drawing the cache. We want to 0 the cache to mark the tiles as drawn. So we're clearing A2 in that case, resetting that tile to 0 so it's not drawn next time. Now we've got a tile number that we do want to draw to the screen, but we're adding the value in A5, and this is effectively a tile number offset. You see the Chibico character, tile 1 in the Chibico character and tile 1 in the background are not the same pattern data. Even though each of the tile maps is only 0 to 255 as valid tile numbers, we are able to specify an offset within the actual complete defined patterns to use for each of these objects, and so we're adding A5 to that to do this. Now what we're then going to do is we're basically going to define our tile in VRAM. So what we need to do is we need to select the VRAM destination. We've got a flag in D5 to do this. Now if D5 is 0, which it will be the first time we run, then we need to actually define the VRAM. So we're going to run the prepare VRAM function. It's exactly the same routine as we just saw. It's selecting the VRAM destination. It's the exact same routine we saw before. It's shifting all the bits around and then selecting it using the VDP control port. It's a little bit slow though, so we don't want to do that for every tile if we can avoid it. So that's why we're using a flag in D5 to mark that we need to calculate a new VRAM address. Now once we've got the VRAM selected, all we need to do is move the 16-bit value for the unflipped tile into VDP data. That will draw the tile to the screen, provided it's got no other things other than its tile number. We've already added its offset here. We don't want to define XFlip, and we're not using the extra palettes and things, so that is just fine for a basic tile. Now the 16-bit value that we write is in the format you can see here. So the bottom byte is entirely the tile number. The bottom 3 bits of the top byte is also tile number. We've got horizontal flip, vertical flip, 2 palette bits, and a layer bit, which defines how the tile is affected by the sprites. Do the sprites go in front of this tile or behind them? And that can be used for simulated parallax and things. So that's the extra options, but we don't need any of them here, so we're just writing our tile into VDP data. Now doing that will actually auto increment the VRAM destination, so we don't need to run prepare VRAM for this. So we simply we're calculating what the next VRAM destination would be in A6, but we don't need to select it next time. We've already moved to the next tile in our tile map here. We're then decreasing our tile count and repeating until we've drawn this entire strip. Once we've drawn our entire strip, we return. However, if our tile was blank before, then we've got a bit of a problem. You see, we're not going to write anything to the screen, so we're updating our VRAM destination here, but we actually, when we write again, we would actually write to the same destination. So we're clearing D5 our flag, and so next time we test D5 we will know that we need to prepare VRAM. We could also prepare VRAM here, but if the entire strip is empty tiles or almost empty tiles, we would select the VRAM destination far more often than we need to, waste a little bit of processing power. So that's why we are using that flag to denote when we need to select our VRAM destination again. On some systems it's possible to read in from the VDP data port, and that will also cause an auto increment, but I couldn't get that to work on the Genesis. I thought that worked on the Master System, and as I say, I'm surprised it doesn't work on the Genesis, because in most cases the Genesis is backwards compatible, but it didn't seem to work for me. So anyway, that's what we're doing there. We've also got the do strip reverse version, which is the X-flipped version. It's very simple on the Genesis, as I say. We've got all this wonderful hardware doing the work for us. So we're reading in our tile number as before. We're adding our A5 offset to our tile number. However, what we're doing this time is we're setting one of the bits, and unsurprisingly we're setting the horizontal flip bit there. So that is X flipping. The tile that we're selecting here, we're then just writing that to VRAM again. We're selecting our VRAM destination again. And then the only other difference is we are moving backwards in our source tile map. So we're subtracting A1 from A2. A2 is our source tile map. So that is moving from right to left through our source character sprite there. So that's what we're doing there. Again, we've got the code here to calculate if we are skipping a tile. It's a different version because, say, this is all one loop here for the reversed tiles. And that's all it is. It's very simple. Really, it's very easy to work with the tile map on the Genesis. You just select the VRAM destination. You just need that routine here or something equivalent to it to convert the VRAM destination, select it with the control port, and then write 2 bytes to VRAM, and you just need to set the bits according to what you want to do. Very straightforward. Anyway, that's all there is to it. Please go to the website, download the source code, the build scripts, and there is, if you want to support my content, you can back me on Patreon. You can also buy my book, which I don't mention very often anymore, which is probably why it's not selling very well. Anyway, I hope you've enjoyed it. Thanks for watching. Use the source code in anything you can. Goodbye now.